Good evening. Welcome to the February 2022 meeting of the Madison DX Club. And we have a special program tonight. Paul KO4LZ is going to be speaking to us about the resurgence of HF. And Paul is a program manager engineer with Rhode Schwartz, and it is a commercial manufacturer of HF equipment and tools. And in the meeting notice, I did include a link to their website. And the reason we're talking about commercial equipment and where the commercial end of HF is headed is that as hams, we've benefited throughout the entire life of amateur radio to what's developed in commercial markets, whether it's Collins or Rockwell or whomever. Even today's SDR owes its genesis to work being done primarily for the military, but also for commercial. So it's a way of looking into the future. It also is a way of hearing that HF isn't gone, it's not forgotten. And I'm hopeful that we'll see a resurgence of it as we find that redundancy to the internet is not only going to be a good thing, it's going to be essential. So Paul, welcome to the club, and I'll turn it over to you.
Thanks, Kevin. Can everyone hear me okay, first of all?
Yep.
Yes.
Fine.
Okay, perfect. So I'd like to start off really short introduction. Again, I'm Paul KO4LZ, and I work as a product management engineer at Rhode Schwartz. And as Kevin mentioned, Rhode Schwartz is one of the biggest test and measurement equipment manufacturers. So things like spectrum analyzers, network analyzers, oscilloscopes. As a matter of fact, if you look at got one here somewhere, my QSL card, you'll see a Smith chart on it, sort of a tribute to what I do as my day job. But we also do HF radios. And one of the things that we got approached about a couple of years ago, I guess, before COVID anyway, I was at the Association of Old Crows show in Washington, D.C. And this is the electronic warfare trade group, if you want to call it that. And there was a lot of interest in HF. And I was asked to do a presentation on HF. Later did a webinar for them and a white paper on it. And trying to decide what to title it, I called it the Rebirth of HF, because suddenly people who had no interest at all in HF, and these are primarily military government type customers and other people, were suddenly interested in HF. And we were a little bit surprised because, again, this has kind of been a niche market for us for a long time. And so I put together a presentation that I'm going to use tonight that's really a two-part presentation. The first part, which is probably going to be old material for many of you, is kind of an introduction to HF. What is HF? And it sets the stage for the second half, which is what I call the rebirth of HF, because HF is really undergoing a resurgence. The amount of interest in HF has been enormous. And this is interest on the part, again, of primarily military and government organizations. And as Kevin said, and it's very true, there's a symbiosis, if you will, that I'll come back to between the amateur and the professional HF community. And I'm going to point that out throughout the presentation. Again, I'm going to apologize in advance if the first half of the presentation is a bit basic for some people. I will touch on things that are relevant to the rebirth of HF. If there are any questions, I will hang around as long as necessary at the end to answer them. Or if you want to ask them in the chat window, I'll pause periodically and look at those. So I'm going to try to share my screen. Give me one moment here. I should probably, before I do this, I probably should to tell you about my ham background. I've been an amateur radio operator for 30 odd years. I started off as a shortwave listener, listening to VOA and to other foreign broadcasters. Eventually got my license. My call sign is actually the old advanced class call sign, a 2x2. That's why I have the funny call sign. And I primarily do HF on 10 to 40 because I use indoor antennas. And I can't really tune an 80 meter dipole in my attic. I also do a lot of VHF weak signal work, 6 and 2. So that's mostly what I do. Again, primarily a CW and digital person. Don't do so much audio these days, hearing, but that's kind of my ham background. So let me go ahead and try to see if I can share this presentation. And can everyone see this? Could someone chime in and say if you see the title slide?
to do.
Okay, so I'm going to go ahead, and if there are any technical issues because it's taking up my whole screen, please let me know while I'm going. So again, this is the Rebirth of HF. This is actually one of our HF antennas we have at our headquarters in Munich, Germany, which is where Rhode Schwartz is located. And again, the presentation is really two parts, and because of the audience that I have here, I'm going to try to go through the first half a little more quickly than I normally would. And that's this introduction to HF propagation. Essentially, what are the different modes of HF and how it propagates? We're going to spend a little more time on Skywave because that's what makes HF interesting to people. And we'll talk about measuring the ionosphere. You know, during the chat, we talked about solar flux index. We talked about sunspot numbers. We'll talk a little bit more about that as well. And again, I'll try, given the audience, to talk about how these relate to the rebirth of HF and not just have a tutorial on HF. The second half is going to be on HF communications. How is HF used? Again, keep in mind, I developed this presentation really for non-hams. We'll talk about traditional HF applications, how HF has been used in the past, say prior to 10, 20 years ago. We'll talk about the decline in HF. And again, decline in HF is basically a loss of interest in HF in the military government community. And then the rebirth of HF, which is, of course, the interesting part of this, because I really think you'd be hard-pressed to find anyone in that community who does not believe that a rebirth of HF is going on. And we'll talk about some of the new, more interesting things that are enabling this rebirth of HF. So again, really quick about HF. Again, I apologize for the tutorial. People define it as 3 megahertz to 30 megahertz. Realistically, this could be extended down. We were talking about 160 earlier, down to a couple of megahertz or 1 point something megahertz. And again, wavelengths on the order of 100 meters to about 10 meters. Again, nothing new here. Some people refer to this as shortwave. You'd be surprised how many people that are not hams still refer to HF as shortwave. The main interest and what we'll dwell on and the reason for this rebirth in HF is that it enables worldwide communications. And we'll come back to this many times. Broadcasters, somebody was talking about VOA before, obviously. Although that has faded, I'm really sad to hear about the World Radio and TV Handbook going away. That's really sad. Government, military, this is where we see a lot of the interest coming from for reasons that I'll get into. And of course, amateur radio. And I'll point out the gentleman here. I'm not sure if you're familiar with him or not. This is Dr. Ulrich Rode, N1UL. He is the son of one of the founders of Rhode Schwartz. He's an IEEE fellow, and he's a very active ham radio operator. If you look for his call sign, again, N1UL on 20 or 40 meter FT8, he's actually running there fairly often. And Dr. Rode, aside from being one of the owners of Rhode Schwartz, and again, a very respected engineer, is actually or is credited as being one of the founders of software-defined radio. So a very technical guy, a very avid ham radio operator, and quite an activist. So we're happy to have him at Rhode Schwartz from the point of view of HF. And again, what we'll talk about in this part of the presentation is the propagation, because it's the global communication aspect that makes HF interesting to our again, military and government customers. But really quickly, no surprise here, right? HF propagation is variable. It's not constant. And the challenge usually in HF, as you all know, is finding the right frequency to reach a certain destination given the current propagation conditions. I would like to talk to some station in Argentina on 20 meters, this point in the solar cycle. When should I do that? You know, maybe use gray line. What frequencies should I use? This is kind of the trick, and this is somewhat complicated. There are 3 main modes of HF propagation. There's line of sight, which is somewhat self-explanatory. We'll talk about that more. Ground wave, and then the interesting one, at least from a point of view of the rebirth of HF, is Skywave. The line of sight, nothing special here, right? Signals propagate more or less in a straight line between transmitter and receiver. This kind of propagation is fairly constant. If for reasons that are not clear to me, you want to use 20 meters to talk to somebody a couple miles away, you can probably do that anytime, day or night. It's not really a good choice for line of sight communications, HF that is, and it's almost never used this way. There are a couple of reasons for this. First of all, large antennas. Obviously, the antennas are very large compared to, say, VHF or UHF. It's a very limited bandwidth. I mean, if you think about it, really, I mean, all of HF is about 30 megahertz. So there's a limit to how much you can actually send in that bandwidth. Much higher noise as you go further down in frequency, as the people on the 160 know, noise gets much worse. Ground wave is the other mode. Ground wave is actually one of the modes of HF that's, I wouldn't say ever really went away. And ground wave signals propagate along the Earth's surface. I've had people say the Earth it conducts along the Earth. This is really not quite true. In ground wave, what happens is the wavefront is tilted forward by its interaction with the ground, so it allows it to travel further than it might normally travel. Ground wave is very dependent on a lot of things. First, the surface conductivity. Come back to this in a second. The frequency, and generally speaking, the surface conductivity part of it is more conductive it is, like salt water, the better it works. And this is why HF, or I'll call it ground wave, really it's water wave, is used a lot for ship to ship and ship to shore, because this mode of propagation actually does work fairly well. And in this aspect of HF really has never fallen completely out of favor. The lower you go in frequency for a ground wave, the better it works. Theoretical, if you're doing math, and we all know that theoretical doesn't really mean much, but 7 megahertz, you get about 35 kilometers over land, about 250 over sea. You go up to 30, it goes down to 13 and 107. So low frequencies over water, HF, still works pretty well and is still reasonably popular. But the really interesting one, and this is why we see the rebirth of HF, is Skywave, because it enables what we call beyond line of sight communications. Signals are refracted. I constantly have to correct myself and other people not to say reflected by the ionosphere, it's refracted. And this propagation is basically a state of the ionosphere. What you're able to accomplish on Skywave depends on what state the ionosphere is in. And as we'll see, this is one of the things that complicates HF and is one of the reasons that HF kind of fell out of favor. Another one that's really important, I added this slide later because people kept asking, is the incident angle. In other words, at what angle does your signal intercept the ionosphere? And this depends on antenna type, installation, height. If you have a lower angle, it yields greater distances. Sometimes you don't want a low angle, NIVIS or NVIS, if you're familiar with that. People want very high incident angles. But generally speaking, lower angles are better. The problem is, of course, as you all know too, there's a skip zone where you may not be able to reach people via Skywave or via ground wave. And this is problematic for HF as well, that you might be able to speak to someone halfway around the world, but not in the next state over. So again, you can see that HF from the point of view of someone who doesn't do this as a hobby is somewhat complicated. So let's talk about ionization for a moment, because ionization is what enables the interesting skywave propagation. Ultraviolet energy from the sun can detach electrons from gaseous atoms or molecules. Most of the gases in the atmosphere, by the way, are molecules, not individual atoms. So you have like N2 and O2. But in any case, the solar radiation detaches the electrons, as you see here. So you have a positive ion and, more importantly, a free electron. And basically, the more sunlight, the more ionization, the more free electrons. When this energy is removed at night, the ions recombine. So the electrons rejoin the molecules, and everybody goes back to being neutral again. This recombination is slower than ionization. So this is why, for example, at night after it gets dark, you still get decent conditions for a little while, because the atoms are split very quickly by the sun, but it takes them a little bit longer to join again. So the electrons are free a little bit longer than you might expect. And again, as ionization will increase rapidly at dawn, but after dusk, it takes a little while to die down. So these different layers of ions create the ionosphere. Again, I know this is a review for most of you, but they're layers of ionization that vary by altitude. And these aren't really layers. They're not lines that have firm levels. They're sort of regions. And there's one of them, the D layer, which is about 60 to 100 kilometers. Numbers are all over the place. There's the E layer, about 100 to 125. And then the F layer, or layers, from about 200 to 275. And the reason that we're bringing these up is these different layers of the ionosphere affect HF signals, as you know, in different ways. Now, I want you to take a minute here, because again, we're all ham radio operators and all do DX. And although this may seem easy and simple and something that you know very well, look at this from the point of view of someone who's not doing this on a daily basis as a hobby, and imagine the complexity that this involves. Let's talk a little bit more about why this is complex. For example, we have the D layer. This is the lowest layer in the ionosphere, and it basically only exists during the daytime hours. It goes away, and the density, though, these free electrons is actually too low to refract HF signals. So the D layer is essentially not our friend if we're trying to do Skywave. it absorbs the HF signals, and this is higher for lower frequencies. So this is why you can use 10 meters in the day and not 80 meters during the day, usually. Absorption, of course, because it's based on solar radiation, freeing ions is highest at midday. And again, as I mentioned before, this is why you can use higher frequencies during the day and lower frequencies at night. The E layer is the next layer. It can theoretically refract signals back to Earth at HF. It usually doesn't. It's a very thin layer. It kind of disappears at night. It's kind of there and not there. It can be used for HF, but really, as a lot of you, especially the VHF people, know that E layer is super important for VHF because it helps support things like sporadic E that are really fascinating when they occur. But for the most part, we can more or less ignore the E layer for HF propagation purposes. The F layer, again, during the night, it's one layer. It splits in the daytime into two layers. I have to admit, in 30 years of being a ham, I'm not sure why that's terribly relevant. The height of these layers changes a lot. It varies a lot based on the ionization. F1 is basically for daytime short to medium, and F2 has the highest altitude. So this is the one that usually it gets used for most long distance HF. Again, the main takeaway, because you're probably all familiar with this, is keep in mind how variable and complex this medium is compared to things like VHF or satellite, which we'll come to later in this presentation. Another aspect that complicates using HF for other than hobbyist type purposes is the I call them the muff and the luff. Remember that absorption and refraction is a function of signal frequency. And generally, I was always taught when you're using Skywave, you want to use the highest frequency possible. So if you can use 10 meters, use 10 meters, don't use 80 meters. This is the maximum usable frequency. There are a lot of maps these days where you can actually see what the muff is all around the world. Signals that are greater than muff go right through ionosphere, go off into space. This is bad. Signals, basically, as the muff increases, ionization increases. They increase together, rather. There's also something called the luff, the lowest usable frequency. And this is the lowest frequency you can use. Most of this is actually due to attenuation and absorption. You can improve the luff by using more power. You can't improve the muff. So what we're trying to do when we use HF is find a frequency that's somewhere between the luff and the muff, right? Between the maximum usable and the lowest usable frequencies. Again, there's not much you can do about the muff because it's a function of the ionosphere. Luff is essentially a function of noise. So the muff is what it is. The luff you sometimes can improve based on your antennas and powers, etc. Again, keep in mind from the point of view of someone who doesn't use HF as a hobby and simply wants to use HF to communicate, how complicated this must all seem. Another one is the critical frequency. Let's make this even more complicated. How do we figure out what the muff is? Well, there's something called the critical frequency. This is measured typically using something called ionosons. They transmit pulses vertically and at different frequencies and see how long it takes to come back and use that to estimate the heights of the different layers. Once we get to the critical frequency, again, this pulse goes right through the ionosphere and it's not returned. And this is how we can figure both the height of the different ionospheric layers, but also the critical frequency. As we'll come back over and over, what is the critical frequency? It changes constantly. Depends on where you are. It depends on the state of the ionosphere. So this is not something you can simply know. Usually the muff depends on who you ask, 3 to 5 times the critical frequency. So again, a very complicated thing. As an amateur with lots of experience, you can say, hey, it's 2 p.m. in July and the sunspot, sunspot number is 100. I'd probably have a good chance of reaching Europe on 20 meters. This requires a lot of time and experience that, frankly, as we'll get to it later in the presentation, most military government users don't have and have never had the chance to develop. So how do we quantify the ionosphere? I mean, we're interested in Skywave because Skywave enables global communications. We see that Skywave propagation is a function of a lot of things, but primarily it's a function of the state of ionization. So how do we quantify this? How do we know what state the ionosphere is in? Critical frequency, as we just talked about a minute ago, is an active measurement. In other words, we send pulses and we see how long it takes them to come back. There are 3 passive methods for quantifying the ionosphere that we can quantify it in 3 ways without having to transmit anything. The first of these is sunspot numbers, which I think everybody's familiar with. Sunspot numbers predict the level of ionization. There's a strong correlation between sunspot numbers and ionization, but it's still a prediction. It's not a firm relationship. There's something called solar flux index. This is a measure of the level of ionization. We actually measure how much ionization is occurring. Again, we'll cover all these in more detail. And then there's the geomagnetic indices. We'll come back to these that indicate the impact of solar particles on the Earth's magnetic field. This again is important for understanding propagation and what you can reach and what you can't reach using HF. And again, we can use these quantities together to give us a good idea of the state of the ionosphere and what we're able to do. Usually most days I go to QRZ and I look at, okay, SFI, sunspot number, SFI, A and K indices, and I go, okay, I'm just not gonna even try today. Or, hey, I gotta get on the air right now. And these measures are very useful because again, if we want to establish worldwide communications with Skywave, these numbers are gonna very strongly influence our ability to do that. So let's start with sunspots. Sunspots are relatively cooler surface regions of the sun. Relatively is 3000 Kelvin versus 6000 Kelvin. So still freakishly hot, but cooler. Sunspots generally last between a few days and a few months. And one thing I don't think I put in this presentation, the sun rotates as a gaseous body. So if you see a sunspot about roughly a month later, I think it's 27 days later on average, that sunspot will return again if it hasn't faded away. Sunspots are important for us as HF users because it's associated with powerful magnetic fields. And these magnetic fields correlate pretty strongly with solar activity and radiation. So if we look at the sun and we see a bunch of sunspots, we know, hey, probably a lot of solar activity. That means higher ionization and better HF conditions. And I think I just said that. Okay. Now, sunspot number is the most important one. We talked during the chat before about sunspot number in the solar cycle. Sunspot number is a daily measure of sunspots. What some people don't realize is it's not just a simple count. We don't just simply look and go 1, 2, 3, 4, 5, 6. It factors in things like the size of the sunspots and the grouping. So it's not just a simple count of the number of black spots on the sun. It's recorded at various solar observatories around the world. Hopefully they all get roughly the same number. They should. The values range from 0, as you've been looking for the last couple years, range from about 0 to I think 250 on was the max ever recorded. And as I mentioned before, more sunspots mean better HF propagation, all other things being equal. This is an interesting tidbit. Sunspots have been counted and recorded for about 400 years. And I put an extra slide in here for this meeting because I would have people say, how on earth did we count sunspots 400 years ago? Visual observation. So here's a picture from a very old book, Maculae in Sole, spots on the sun. If you look, the year here is 1611. Okay, so that's more than 400 years ago. And you can see someone, I don't know how they did this. Hopefully they didn't just stare at the sun, but actually recorded at different dates the position and the number of the spots on the sun. So we actually do have records of sunspots, the number and the position and their dates going back over 400 years. Now, as we talked about, and we're all very interested in as regular users of HF, there's this sunspot cycle that's roughly 11 years. It varies. At the peak, and depending on how old you are, you may define this differently. The sunspot number is about 150 and propagation is good, even at higher frequencies. This is the, hey, I worked South Africa on 10 meters with 5 watts from my car while I was driving kind of thing. At the bottom, sunspot number is 0 and propagation is poor, especially at high frequencies. Not many people working South Africa from the East Coast on 10 meters these days, just the function of sunspot number. It's generally good for long-term prediction. It's 11 years and the resolution of it is pretty poor. One thing I should point out, which both intrigues and terrifies me, is that because we have this 400-year record of sunspots, we also know that at several points in history, so during the late 1600s and I believe the early 1800s, sunspot numbers basically were stayed low or 0 for decades. These are the solar minima. I think they were called the Dalton and Maunder minima. But there's some concern, or there has been concern, that maybe we're heading into one of those again. I hope not, because I don't have several more decades to be QRV. but this is something that happens. So long term, there are factors influencing propagation that are cyclical and that, frankly, we can do very little about. The next one I said is a solar flux index. So sunspot number is an observation. We look at the sun, well, not directly look at the sun, but we look at the sun and record sunspot numbers. Solar activity can also be quantified by measuring the solar flux at 2800 megahertz, or about 10.7 centimeters. Obviously, we haven't been doing this for 400 years because the equipment didn't exist, but it's been around for quite a while now. I'm trying to think how far back it goes, decades. And this is reported as a solar flux index. It's measured in the creatively named solar flux units, and these are in the range of about 50 to 300. Again, remember that this is a measurement, not an observation. So it tends to be more consistent and reliable. And luckily, unfortunately, though, rather, it doesn't have this 400-year history of values. So we still have to rely on human observations to get this long-term information about the 11-year solar cycle. It does correlate really well with sunspot number. This equation, the 73.4 times 0.62 times, so it actually works really well. Just try it sometime. It's usually pretty darn close. So there's a strong correlation between solar flux index and sunspot number, generally speaking. And just like sunspot number, higher solar flux index, higher MUF, better propagation. The other interesting thing we have to talk about is solar flares. So the ionosphere is affected by solar radiation, a long-term, short-term, et cetera. But when I say short-term, I mean days. They're also short duration events. So like solar flares. Solar flares are generally bad. These are eruptions that increase radiation and also eject low and high energy particles. We'll come back to the difference between those. These are generally unpredictable. Some people say there's disputes about this, that they're more common during peaks in the sunspot cycle, but we'll just say they're essentially unpredictable. Solar flares are bad because they can lead to three main things, at least bad from a radio point of view. Sudden ionospheric disturbances, polar cap absorption, and both geomagnetic and ionospheric storms. So again, these are things that further complicate. If it wasn't already complicated enough, trying to figure out what frequency I can use, where are we, the solar cycle, time of day, et cetera. Now we have these somewhat unpredictable events and what they can do. So let's talk about SIDS, sudden ionospheric disturbances. Remember that the sunlight takes about 8.5 minutes to reach the Earth. So if the sun disappeared 8 minutes ago, we'd just be finding out about it right now. The delay or ionization, which is what absorbs signals, increases because there's all of this solar radiation. Remember, the delayer acts as an absorber and basically kills HF propagation. It only impacts the sunlit hemisphere, right? Because only that side of the planet is exposed to the solar radiation. And it typically is very short duration. It maybe lasts an hour and then things get back to usual. So if you see a solar flare, you're probably not going to be doing anything for an hour or so, but later that day, maybe. Some flares can enhance HF at very high frequencies, again, because of the increased ionization, but generally, these are undesired situations. The other one is polar cap absorption. So remember that a flare consists of solar radiation that takes about 8.5 minutes to reach the Earth, and these low and high energy particles. So the high energy particles take a few hours to reach the Earth. And when they do, because of their magnetic field, they enter near the poles. They kind of get wrapped in towards the poles. And this increases the delay absorption in the polar regions. So not everywhere, not in the sunlit hemisphere, but merely at the polar regions. This, however, can last for several days. A SID hour, a couple hours. Polar cap absorption can last for days. And it blocks HF near the poles, which is a problem, especially if your long path goes around the pole or goes that way. You may have other paths if you're pointing in a different direction that are unaffected. It's important to, we'll come back to why polar cap absorption is particularly important as a problem later in this presentation. But keep in mind that it only affects things at the poles. The third problem is these geomagnetic and ionospheric storms. The high energy particles get to Earth a few hours later. The lower energy particles, being lower energy, come to the Earth maybe 20 to 40 hours after a flare. These can also be created by something called a CME, a coronal mass ejection. One thing I should point out too, that whether or not a flare or a CME is a problem, partly depends on the orientation of where that flare occurred on the sun and where the Earth is. You can have a really nasty flare in CME, but the particles are thrown out in a direction the Earth doesn't actually pass through, which is not a bad thing. when you have these lower energy particles, these can create a geomagnetic storm that create these nice aurora. That's where they come from. They can also cause problems. I think everybody's heard the stories of space weather and messing up GPS, satellites, overloading power distribution networks. There was a very famous case of that in Canada a while back. So can cause problems other than radio problems. Geomagnetic storms also create an ionospheric storm, and it's the ionospheric storm that lowers the muff and degrades propagation. So here again is something else that can go wrong with HF. So if you take a moment again to look at someone who's looking at HF as a reliable way to send lots of data anytime, anywhere, under any conditions, you see that this is very challenging. And the reason I start this presentation with talking about HF propagation is you realize the enormity of what this is in terms of having a reliable communications medium, and especially one that's going to be operated by people who don't do this as a hobby and don't do it all day, every day for decades. So I want to talk for just a minute about the A and K indices. Again, you are probably familiar with these. These measure the magnetic fluctuations. Basically, lower is better. If you look at that little widget or whatever on QRZ or other places that show A and K, you see they're 0, that's great. You see they're really high, that's bad. These are measured around the planet, so usually they're reported as AP and KP. That's P is for planetary. And A is calculated every day and K about every 3 hours. And that means that K indicates what's going on right now, and A is a longer term measurement. So I'll just really quickly summarize HF propagation. Again, remember that Skywave is used for global communications. Signals are refracted or absorbed, depending, by the ionosphere. And this is a function of both the frequency of the signal and the state of ionization. So ionization increases during daylight when the sun is actively hitting that part of the atmosphere, when there are more sunspots, and of course there are these solar events we talked about that can disrupt the ionosphere, things like solar flares, CMEs. And we use 3 metrics, 3 passive metrics, so sunspot number, solar flux index, and the A and K indices to quantify the ionosphere. So again, if you've been doing HF for decades, this may all be review for you, but you can see how your head would be about to explode if you're trying to think about using HF, and why perhaps HF began to decline in its popularity, which is the second part of this presentation. I'm going to pause for a minute here and see if, okay, I don't see any questions yet. So I'm going to just continue on if that's all right. So why did HF decline? I mentioned at the beginning of the presentation that HF declined, and I would think you'd be hard pressed to find anyone who would disagree with that from a commercial, government, military point of view. Why? Mostly it's satellites. Satellites began to replace HF in about the late 1960s. And there are a lot of reasons for this. The first of all is satellites could provide much higher data rates. Remember that the bandwidth at HF is very limited. All of HF is barely 30 megahertz. That's not a lot of bandwidth by today's standards. Where if you have a satellite that's operating in the L band, like around a gigahertz or so, they have a lot of bandwidth that they can use. This is the big one. It's relatively immune from that variable propagation that we just talked about. If there's one takeaway from the first part of this presentation is that HF propagation is super variable, and it's not a guarantee, and it changes constantly, and you have to adapt and account for all kinds of things. Satellite doesn't matter, right? I mean, a satellite can pretty much operate the same way regardless of what's going on with the sun, the ionosphere. It makes no difference whatsoever. And the corollary to this is it doesn't require trained operators. If you want to use a sat phone, you pick up the sat phone, you type in the number, and you talk to people. It's not like, okay, let's see. Again, it's a Wednesday in July at the midpoint of the solar cycle, and my antenna will do anything between 20 and 80 meters, and I'm trying to talk to somebody 1,000 kilometers away. And here, obviously, there's knowledge involved. The other problem with HF would cause it to decline is this change in expectations on connectivity. Someone mentioned this during the chat, right? You basically expect high data rates, instant communications, always on, available everywhere. So people's expectations is I should be able to send and receive relatively large amounts of data all the time whenever I want to. And of course, traditional HF didn't do that. The internet's becoming more and more globally available. We're talking about Elon Musk's constellation. You can pretty much get the internet anywhere nowadays. And so this decline in HF use, mostly due to satellites and increased expectations, which led to a decline in funding. and a decline in mind share. And there were fewer and fewer people who had a knowledge and a practical experience with HF. And so it was kind of a vicious cycle that as fewer people knew about HF and used HF, there's less interest in HF, and it just got worse and worse and worse. So this is really, in our experience, what kicked off this decline in HF. That said, all is not wine and roses for satellites. Remember that we're talking about HF versus satellites, because satellites really, again, from a government military point of view, are what replaced HF, starting probably in the 70s, really. There are a lot of ways to do bad things to satellites. There are a lot of ASAT, anti-satellite technologies. If you are a country that isn't able to launch things into space, not a problem. You have ground-based lasers and other ways you can mess with satellites. There are both air and space-based kill vehicles. When I first did this presentation, it was only the Chinese who had blown up a satellite and filled orbit with junk, and the Russians just did it recently to test these kill vehicles. Satellites are also very susceptible to jamming. Obviously, HF can be jammed as well. I lived in Europe during the Cold War. The jamming of HF is definitely doable. Satellites are a lot more vulnerable to it. First of all, satellites aren't frequency agile. Most satellites have a limited uplink, downlink frequency or fixed frequencies, so it's very easy to jam them. Think about HF though. HF, if someone is jamming you on one band or you're being QRM'd on one band, you QSY to another band. The other one is these solar storms and space weather. These are problems, right, for HF, things like solar flares. They're problems for satellites as well. Flares and CMEs can also disrupt or damage satellites. Now, if you have a really bad solar flare or a really bad CME, yes, it can cause a complete HF blackout, but the ionosphere will come back. Your satellite gets damaged, it doesn't fix itself. So this is a problem. There's also one thing that's important is a lack of polar coverage. I mentioned before about polar cap absorption and why that's important. No matter how you feel about the issue of climate change, there's no question that the polar region, especially the North Pole, is becoming more and more navigable over time. The Russians in particular, if you read the news, are very interested in having a north path through the polar regions for shipping. Because satellites don't have polar coverage, or they can have it, but it's very expensive, it's not typical. There's more and more need as time goes on to have some kind of global communication that works in polar regions. And this is a place where satellites don't work particularly well, or if they do, they're very expensive because fewer satellites cover those regions. Again, not all constellations. I think Intelsat covers a pole, or Inmarsat, I can't remember which one, but most of them don't cover it or don't cover it well. There are other vulnerabilities. Terrain. If you're using a sat phone from the middle of a canyon or a cave, that's problematic. HF, a little bit more flexible in that regard. So satellite, although it has a lot of benefits for it, has a lot of problems with it. And over time, people have begun to realize that this is a problem, or that they need to find some alternative method to communicate if the satellites don't work. So this leads to basically to the rebirth of HF. Global connectivity is mission critical. If you can imagine the military not being able to communicate over long distances, or the gentleman who was in the Foreign Service, embassies not being able to phone home because satellites are down, or they're being denied use of their satellites, what's a good fallback? Well, HF. This backup and redundancy has become critical. It's not a nice to have nowadays, it's a must have. HF in this regard has a lot of advantages. It has truly global coverage. Unlike satellites, there's no limitation on commuting with someone at the North Pole. I've worked Antarctica with my very modest station here from North Carolina. It's easy to do on Gray Line. That there's no part of the world that's less or easier to work. I shouldn't say that, I'll get in trouble for that. Generally speaking, you can reach any spot on the globe using HF. It requires no infrastructure. You don't have to launch very expensive satellites and have a ground-based infrastructure to communicate with them. Your infrastructure is the ionosphere, which essentially is free and essentially indestructible. You can't destroy the ionosphere. You might be able to mess it up for short periods of time, but you can't destroy it. And it's much, and when I say much, it's much cheaper than satellites. The most expensive HF setup is still orders of magnitude cheaper than satellite. And as I mentioned before, it's robust against attacks. Yes, you can jam HF. There was some jamming of HF apparently going on in Cuba recently, but it's much more robust against attacks than satellite. And as I mentioned before, it's robust against jamming because partly HF is frequency agile, and we'll come back to this as well in a few moments. So what are the things that enable the rebirth of HF? There's four things. First, do we need improved data performance? Basically, if you have a 3 kilohertz channel and can send data at 1200 baud, that's not going to cut it, not as a backup for satellite. So in order to have this rebirth of HF, you need higher data performance. You need improved audio quality. Again, people have higher expectations now of audio quality, and HF is really kind of lagging the traditional analog HF sideband. Approved availability. Can I use HF at any time I want to and be able to reliably set up a connection with someone anywhere in the world? That's kind of a requirement as well for HF to have this rebirth. And the last one is improved operation. I mentioned that there's this vicious cycle with HF operators disappearing over time. And how do we make HF so that people who don't do this as a hobby and don't have decades of experience or years of experience can actually use it reliably? So these are the four things that need to be addressed to have a rebirth of HF. And this is what we're going to talk about next. So I'm going to group availability and operation into one category. Basically, remember before, the issue with HF mostly boils down to what frequency should I use, right? Choosing the wrong frequency, it doesn't matter how much power you have. Well, okay, that's also not completely true. But generally speaking, you are limited to using certain frequencies to reach certain parts of the world at certain times of the day under certain conditions. Again, trained and experienced humans, and I would say everybody on this call in this regard is a trained and experienced human, used to do this. There are also tools that you can use, propagation prediction tools like vocap, where you can plug in and say, okay, what's the frequency I should use if I want to talk to these folks? But what the ITU came up with, realizing this doesn't scale and that the operators simply aren't there, came up with something called adaptive HF, and there's a whole ITU recommendation on it. And basically their suggestion for adaptive HF was, let's have a system where you automatically have the frequency selected based on things like Sunspot Number and MUF and LUF and other things. You automatically establish the communication. So you're not just calling, hey, CQ, 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 or you're not saying, K21LJ, this is KO4LZ. It does establishes automatically, and it automatically adapts to congestion. You can read jamming in here too, and propagation changes. So basically, wouldn't it be nice if HF, you could just simply say, hey, I want to talk to this station, punch a button, and your radio says, okay, this is the right frequency to use. It sets up a communication. And if somebody starts QRMing or jamming you or propagation changes, it'll automatically QSY to some other frequency. So you can see that if you had a system set up like this, this would really help enable the use of HF, because again, you don't have those trained human operators who can do this automatically. The way this is established for military government customers especially is ALE, or automatic link establishment. I will stop and say here, there is a ham version of this, is PC ALE. Frankly, I don't know many people who use it, but so we're going to just kind of limit to regular ALE. So ALE, basically stations are assigned and are called by an address. So you basically punch in the address of the station you want. If the station hears itself being called, and when I say the station, I mean the automated function of the station, it tries to synchronize with the calling station, set up a communication, and the frequencies are chosen using something called link quality analysis. What this basically means is the stations periodically transmit a sounding signal and their address. So imagine me, be irritating for me to do this on 20 meters going, this is Kilo Oscar 4 Lima Zulu conducting a test. And then maybe 15 minutes later, this is Kilo Oscar 4 Lima Zulu conducting, and I keep changing frequencies. Well, somebody who's listening might go and say, hey, every day in June on 20 meters at 8 p.m., I can hear KO4LZ. That's the frequency I should use if I'm trying to reach him. This is essentially how link quality analysis works. Stations scan and they measure and record the signal when they hear it and the level, and they use this to build up a database. So I've done this. I'm sure everybody's done this when you're hunting rare DX or not rare DX. You start saying, when is this guy QRV? When is he on the air? When can he be heard in my part of the country? Maybe you use something like PSK Reporter or something like that if you're using Digimodes, or the reverse beacon network, right? You can say, hey, this station heard this station at this time, and I'm near that station. Maybe I can use him. ALE also has the ability to listen to determine if a channel's in use. This is the rule listen before transmitting, which we all know and respect, and can adapt if conditions change. If you were, again, to use a ham analogy, If you get stepped on by some automated pack core station, you would just simply QSY. And ALE allows all of this to happen automatically. The human operator really doesn't have to do anything. So you can see why this would be useful in enabling a rebirth of HF, because essentially someone who's untrained can push in a free address and have the radio do the hard work of creating and maintaining a connection. So there are various generations of ALE. The first generation ones were all proprietary, no surprise there. There was by the way, these 2Gs are not the same Gs as like 2G, 3G, 4G, 5G. Okay, these are just generations. 2G ALE was the standardized version. This was a big deal because now radios from different manufacturers can interoperate. There's also a 3G ALE that basically was some improvements like faster setup under noisier conditions, and it was more spectrum efficient, which is really important at HF because bandwidth is very limited. And it was also more scalable. So 3G ALE was a huge step forward. The other thing that we need to talk about in terms of re-enabling the birth of HF is modulation. So what I'll call legacy HF modulation is a 3 kilohertz channel, right? This is what we all use on sideband. And you can have a modem that sends data over what I'll call a voice channel, over that kind of channel. So one of the advantages, right, of FT8 is it uses much narrower bandwidth. But if you're using something like RTTY, for example, you're usually using the whole channel, right? Modulation type has changed over time for HF. So originally you have, I mentioned RTTY, you have FSK, right? And even PSK, I'm sure people remember PSK 31. These were traditional digi modes. And over time, there have been different modes. So MFSK, so FSK with more than just mark and space. These modes became more popular, things like Piccolo. I'm trying to think of other examples. JT65 is another example. FT8, for that matter, is an example. For military government, for these newer versions of HF radios, they use things like QAM, quadrature amplitude modulation, if you're familiar with that. So basically amplitude and phase keying. And even multi-carrier systems like OFDM, which are used in cellular and Wi-Fi, and cable modems nowadays also use OFDM. So attempting to leverage some of the new technologies for radio systems in HF as well. And again, the reason that we're doing all this is to improve the throughput that we have. Another part of the change from legacy HF that's enabling this rebirth is instead of setting voice as analog, right, as the sideband is AM, essentially, single sideband AM, voice is sent digitally over data channels. So someone was talking about DMR earlier, or D-Star, as a similar concept, right? We don't send the voice as analog, we send it as bits. And this gives us some advantages in terms of quality and bandwidth and efficiency. So how do we improve this HF bit error rate? Right, we want to send things as bits. Well, I mean, some of those bits are going to be errored. And frankly, HF is a horrible environment for sending data. It's noisy, it's variable. You have burst errors, you'll have sudden fades. You have a whole bunch of QSB or QRN or something, and all of a sudden you lose a whole bunch of bits in a row because there's this fade in and fade out. So HF is really an absolutely awful environment for trying to send digital data. But we have to find a way to do this, to enable this rebirth of HF. In traditional legacy HF, this wasn't easy to do. It wasn't easy to detect bit errors or correct them. If you ever used, well, RTTY is a great example, but JT65 even, and you on your screen, all of a sudden you see garbage, right? What can you do about that? Not much, right? The bit errors occur and you lose stuff. And this limits transmission speeds. If we could clock more bits more quickly, we could do that, but we're going to lose more bits because of the environment. Fortunately, there are ways that modernized HF is dealing with this. One is by interleaving. So we basically take the bits and kind of mix them all up and then unmix them at the end so that a burst doesn't take out contiguous bits. There's something called FEC, forward error correction, that can be applied to bits that allows them to detect and correct bit errors. And there's also automatic repeat requests, or ARC, that can be used to automatically say, hey, I was expecting all these bits, I didn't get them, retransmit them. And again, this is happening without human operator intervention because, as I've mentioned several times, HF is a very variable and very unpredictable environment. A lot of specialized knowledge is needed. In order to make HF, to have this rebirth and make it a viable backup for satellite, which is a goal here for those customers, they need to make it so it's reliable and doesn't require a lot of human intervention. And things like FEC and ARC and interleaving help address the bit error issue. There's also something called wideband HF that's super important. I'm just going to touch on it lightly here. No, normally we have our 3 kilohertz channel, which can carry a certain amount of data. We could add another channel, right, and scale it that way. We can simply bond channels together. Usually, though, a single larger channel provides better performance than having multiple smaller channels together. So we'd like to be able to have a wider bandwidth for our signals. For example, if we were to widen out our bandwidth, as is done in this mill standard wideband HF, excuse me, we could have up to 48 kilohertz in various steps. So you maybe have 32 kilohertz or 24, but up to 48 kilohertz. Think about how wide that is compared to a traditional sideband 3 kilohertz channel. This would allow you to have data rates of up to 240 kilobits per second, or about a quarter of a meg. This may not sound like much, but if you compare it to what even the best, say, PACTOR modems can do, it's an amazing amount of data. And this is viable. I mean, 240 kilobits per second, you can actually send data. Like you could actually send a file or a picture. And I don't mean a picture like SSTV type picture, I mean a real picture. And you could also send various textual information. So it is possible to do something useful with this. And this wideband HF is one of the enablers. If we were stuck at 3 kilohertz channels and 1200 baud, nobody would be looking at HF as a replacement, or not as a replacement, sorry, as a backup for satellite. But wideband HF gets the data rate high enough that it could be used successfully in a pinch. And that, again, is where a lot of the interest in HF is coming from. And again, having a wider signal makes it more robust in a hostile environment. The wider the signal it is, the harder it is to jam. And this wideband HF is not just a theory. It's been used successfully in numerous military trials. I can tell you that our HF radios and the HF radios of our, I'll call them competitors, have implemented wideband HF. So this is not just something people are thinking about doing. It's something that's actually being used today. So I mentioned before about wideband HF. You can have different modulation types. So you could say, well, I want to interleave. I want to use forward error correction, etc. In wideband HF, there are different ways that you can implement this. You can use standard what's called phase shift keying. There's special QAM, quadrature amplitude modulation. And using these modulation schemes helps improve the robustness and reliability of HF. Basically, higher order throughput, that is more of these little pots on the constellation, basically is higher bit rates. This requires a lot of special processing at each end, but it is possible. And a lot of these technologies, PSKs and especially QAM, are leveraged. The knowledge of them exists because they're used very widely, almost exclusively in cellular. If you're using cellular, if you're using Wi-Fi, it's all QAM these days. Cable modem, same way. You'll see that the constellations, if you're familiar with QAM, these constellations are circular. That helps to reduce the peak to average ratio, which makes life easier for amplifiers and other pieces of equipment. So again, when designing wideband HF, they realized they couldn't just stick with the old mark space, FSK. They had to come up with more complex modulation schemes. And luckily, they've been able to leverage schemes that are used in other radio frequency technologies. So along with this is something called 4G. And again, this is not LTE 4G. This is just 4th generation ALE. They have wideband ALE to go with it. Because think about if we have all these different potential bandwidths, maybe we're using 48 kilohertz, maybe we're using 12 kilohertz. What kind of modulation type? Are we using this constellation type or this one? Are we using error correction? How many subcarriers? Well, if two stations want to communicate, they somehow have to negotiate this or at least know ahead of time. So all of these new nice features of wideband HF require this wideband ALE. So essentially the two endpoints can negotiate or sense what they're doing. They also have the spectrum sensing to determine, okay, I'd like to use 48 kilohertz, but there's some noise here and some noise here, so I'm going to have to only use 24 kilohertz, okay? And then they negotiate that. And again, this is one of the enablers of the rebirth of HF. There are additional features that apply both to the wideband and narrowband HF. I won't go into them here, but that's essentially another enabler is this wideband ALE. So really quick, a summary of these HF communications. Satellite, and again, we're talking about HF being a backup for satellite, largely replaced satellite pretty much completely for global communications. And over time, of course, people realized the need for communications was a must-have, not a nice-to-have, that it wasn't acceptable to simply have satellite be vulnerable and fail. Satellite, of course, has higher throughput and wasn't propagation sensitive, and it didn't require trained operators. It was easier to use. Satellites, though, are much higher cost. And as we mentioned, they're vulnerable. They're vulnerable in a lot of ways that HF is not. So the modernization of HF has really been focused on reducing or eliminating the shortcomings. And by shortcomings, I mean variable nature of propagation, both short-term due to changes in the ionosphere over time, longer term, the solar cycle, unexpected things like solar flares, and then the need to somehow figure out what frequencies should I use, set up communications, and adapt those communications when conditions change. So QRM, jamming, other problems. So the idea is that in order to enable this rebirth of HF, we have to address all of these. We have to either automate them or make them something that an untrained user can use. And this is the point in this modernization of HF. The two of the biggest enablers here are the wideband HF. Wideband important again because it increases the bandwidth, the throughput we can get on HF, and ALE or automatic link establishment, which helps the two endpoints negotiate and set up these connections without requiring human operators to have special knowledge. So that's really kind of the end of the slide part of it. I'm going to take a look here and see if I had any questions come up. It doesn't look like anything's come up yet. So, oh, go ahead.
You haven't unmuted it.
Thought I was unmuted. I assume you were looking at me.
Yes, go ahead, Ed.
This is, well, it's involved in what you're talking about, but it's a little bit off mainstream.
I'm good with all.
I use flex radios with spectrum scopes on them. And every day operating on 20 and 40 meters, we see signals constantly going across the band.
You mean like this?
Yep, you just see this beautiful line go this way and then go that way.
Oh, I see them too.
Can you tell us what on earth that is?
It could be a lot of things. It might be you know, what I call them sweepers, right? They start on one end of the band, they go across the other end. It could be a sounding signal. I don't think it's an HF, an ALE based sounding signal. But typically, my feeling, okay, is that these signals are probably someone's measuring the ionosphere or measuring propagation conditions. It's not somebody tuning up, and it's not any kind of modulation or information. So, and it's not just like random QRM, I don't think. Nothing moves that fast. So I really feel like that's some kind of sounding signal. I have to say, though, I'm not entirely sure myself.
Can we rule out over the horizon radar?
Yeah, over the horizon it looks different. Yeah, the old woodpecker, the old Soviet woodpeckers and things, there still is over the horizon radar, but it's more of a like that. It's not the line that goes across the screen. Yeah, I see that line too. And if it makes you feel any better, I spent years doing interference hunting in the field, like with government, military, like direction finding. We see those things all over the place at different frequencies too. And we would sometimes see them at, you know, like 700 megahertz. You would see, like, what the heck was that? So, yeah, that's the problem. It goes so quickly, it's very hard. And it's usually a very narrow carrier, right? It's not like some wide noise like thing. It's just a little CW looking carrier going.
Very distinct, slow line.
It's fun to grab the VFO knob and chase it. You can chase them quite a ways sometimes.
How far do you see them move, Fred? Yeah, I mean,
I haven't chased any lately because I started ignoring them. You know, they just come by as a blip if you're operating. But I mean, certainly through the whole band that you're on, and then maybe just if you've got a full coverage receiver, just keep spinning, and it'll eventually kind of die down. Sometimes I think they even go backwards.
See, the reason I say that I wonder if that's not an ionosonde or some kind of ionospheric probe is, as I mentioned before, this is how you would measure critical frequency, right? You start off at a low frequency because they always move left to right, don't they? I mean, my experience is they move lower to higher, right? So you start off at a low frequency and start sending a signal. Now you're sending it vertically, but you know, they go all over. And then you keep going up until the signal stops coming back, and then go, okay, that's the critical frequency, right? And if you looked at this as frequency versus power, you would see a signal start low and start going high, right? So my guess is that some kind of ionospheric sounding, and it might be an ionosonde, but I would have, it'd be nice, you mentioned a flex radio. I work for Rhode Schwartz. I have things that can look at all of HF instantaneously in real time. If I ever had an antenna connected to it, I could tell you exactly where it stops and starts. And my gut feeling is it probably starts at 3 megahertz and stops at 30 megahertz or something like that. So I'm assuming it's some kind of ionoson, but I can't say that for sure.
K3ZO. Couple of things you mentioned, very interesting, the whole presentation, but you mentioned lack of polar coverage.
Mm-hmm.
And I've heard that our GPS system doesn't cover the world completely for that reason. And that, for example, if you want to have a GPS system in Tasmania, the island south of Australia, you have to use a Russian GPS system.
Yeah, GLONASS. Yep. Yeah, GLONASS has a higher. Yeah, I'm sorry. Go ahead, Fred. Sorry.
That's the only one that works there, for example.
Yep. So GLONASS, there's an orbital inclination. What is if the Earth's equator is here, what is the angle to the equator that the satellites, the constellation is? I believe for GPS it's 55 degrees. I need to check. And for GLONASS it's higher, partly because the Russian, if you look over Russia is, right, compared to the US, is at a higher latitude. So they put the satellites in an orbit that would have better coverage over Russia. There's the Chinese constellation Beidou. I think they have some that are in a polar orbit. I'm not positive about that. I need to go back and look. But yeah, the GLONASS covers higher latitudes better. Absolutely, it does, because the Russians designed it that way, or the Soviets designed it that way.
And
I think they were Russians at that point. But anyway, go on. Sorry.
The other thing that something you said reminded me of is that supposedly there was the stock market people have figured out that you can use HF to transmit faster computer to computer. You can hit the stock market a few seconds or microseconds earlier if you use HF radio. And there was a couple of transmitters set up west of Chicago, in the Chicago suburbs, to communicate with Wall Street that were faster than wire, something like that. And this is sort of an interesting concept.
I mean,
it's certainly. Oh, go ahead, Nick. Sorry.
Yep. So I work for Flex Radio. So I wanted to say that everything you said in your presentation is 100% fact and true. And especially with respect to, the military does not understand HF. They not even close. When we did a radio trial, it was an across the country radio trial inside of a C-130. The frequencies they reserved for us that day started at 8 megahertz and went up to 24 megahertz at 10 a.m. On the East Coast, trying to get to the West Coast. And I'm like, well, 24 megahertz, that's going to do me zero good here. So, but they do not understand that anyhow. And I did want to say that, so yes, high frequency trading, microseconds matter. And so they will use we have been asked to design high power transmitters, 50,000 plus watt transmitters in the HF region, in the shortwave region. They will buy the frequency, and then they will send a tiny bit of data, because it's faster to do that than it is to go through all of the thousands of miles of fiber and everything.
Mm-hmm. Yeah, that doesn't surprise me. And the satellites would be no faster because you have the problem of the distance, right?
Yep,
the atmosphere is lower than the satellites.
You also have buffering computer to computer, and that is a killer for high frequency trading.
Yeah, the routers, every single one of them is store and forward. And it kind of finds a path to take and says, okay, I can release the data now. So yeah, there is a lot of latency on the internet. And sometimes it's not too bad, and sometimes it's really awful, even when things are working well.
Yeah. So with respect to satellites, the whole day without space is incredibly popular in the Department of Defense right now for people who care. It's a huge deal. It is a massive deal, the day without space. What happens when your satellites get turned off? I mean, people are very concerned about it currently, as they should be.
And that's the whole reason why I've been, I'm a ham. I like HF, but that's why I've been doing this professionally so much, is because there's so much. I mean, just people coming up like, oh my God. Like we suddenly realize that our satellites are vulnerable and we need something. And I don't want to say it's panic, but you have to understand that the military doesn't have a lot of HF savvy guys in it. And this is becoming, they realize, okay, in fairness, because I talked to them, they realize that there's a deficiency there, and they are trying to address it. And again, all the things I talked about are tools that enable them to address it. The solution was hire a whole bunch of hams and put them through basic. They're not going to do that. They need this to work without human intervention as much as possible. And that's what's driving a lot of these developments. And will some of this, I get asked, will this trickle over into the ham community?
No.
Yeah, I don't think so.
No.
Not really. Not wider bandwidths. Not ALE has been kind of, I hate to call it a failure because all of our people work very hard on it, but it's kind of been a failure. It's really mostly a military government application.
Yeah, I mean, so we just delivered a radio to the Air Force, and like the Air Force mantra is aviate, navigate, communicate. A pilot is not like turning a VFO dial. Like, that is not how any of this works. ALE is very complicated. There are so many layers of software. It's never going to transition to amateurs. The most you can hope for is, better radios and higher power, stuff like that. We're never going to run ALE on the amateur bands.
But, and the question I've got is based upon your thought-provoking presentation to them, what HF bands are the government now going to covet that are part of the amateur radio community?
Yeah, I hate to get in. Obviously, I'm super defensive about spectrum allocations as a ham. Okay, so I'm super please don't touch our spectrum. You've taken too much already. I couldn't speak to that. I don't know. I mean, honestly, they're not looking to use it a lot. They're using it as a backup. And really, if things go south and the balloon goes up, they're really not going to care about oh, we need this. They're just going to take it. Okay. And so I don't think they're really concerned about pushing the hams out, because they're not going to use it very often. They're using this one when things go really, really bad, and then they really don't care who they step on. I don't mean that in a bad way. Right? I mean that's the way all allocations work. But that's so I'm not living in fear they're going to take parts of HF away from us. I'm really not, and I'm kind of paranoid about that, frankly.
I've got a comment to make about that. I operate 136 kilohertz and 472 kilohertz, the new amateur bands. And we're limited to 5 watts of effective radiated power. The reason is Russia and China are maintaining their low frequency communication systems. And through international agreement, I guess with the ITU and all, they were able to, get the spectrum released, over most of the world because it wasn't being used. And it's interesting, 2 of the 3 superpowers are still using it and not giving in an inch. I find that very interesting. That's also the 2 superpowers that are working on killer satellites. So kind of a scary situation brewing here.
Yeah, I work for a company that makes antennas that go on submarines. Okay, so a lot of it has to deal with submarine communications too. I mean, if you need to communicate with submarines, you've got to go really, really, really low.
Yeah,
right? And I think that's that's the reason why I think they're interested in that. What I said about HF, I'm not sure applies to LF or MF at all. I mean, I can't speak to that.
It's still military communications, doesn't. And there's a lot of digital stuff down there that is kind of mysterious.
But it doesn't provide the data rates necessary. So
yeah, you're right.
There's already a push to go beyond 48 kilohertz in the HF realm to support even faster data rates.
Yeah, at the very low frequencies like LF, I'm not telling you anything you can't look up online. Okay, basically it's the hey submarine, come up a little bit out of the water so we can talk to you on a higher frequency. Okay, that's how that's. I mean, again, you can look that up yourself. But so they don't need really high bandwidths at those low frequencies. Besides, there's not a whole lot of bandwidth there anyway. It's basically just say, hey, we need to talk to you. Let's QSY to someplace where we can talk. Any other questions about this or really anything else RF? I do HF is actually maybe 5% of my job. So if there's something else,
I'd like to go back, if I may, and try to tie a couple things together.
Please.
I've observed in this last Sunspot cycle, even worse than the previous one, that even despite the numbers, the conditions were a lot worse than the numbers would indicate. And I've talked to other people that have confirmed my suspicion that the geomagnetic problems have been greater in the last few years than previously. I wonder if you've experienced that, or if you look at the numbers, they don't really tie all that together at least in the propagation stuff that we see.
So my personal, okay, not based on data, just my personal operating experiences. Yeah, it's been really awful lately, more awful than you would think looking at the numbers. You look at the Sunspot Number or SFI, and you go, oh, I might have no, you don't. But again, I have a very limited station, so I try not to extrapolate from that, like what propagation conditions are. Maybe, I mean, does anybody else here have that feeling too? I mean, I feel that way, but again, I have a really puny little pistol station. I'm going to take that as silent assent that we are correct here. And
Yeah, it's you and me against the world.
exactly. Yeah, I'll just take that as yes. Now that is my feeling. I'm anxiously anticipating a rise in the conditions over the next few years. I really, really want that.
Has there been an increase in geometric whatnot? You know what I'm trying to say.
Yeah, the A and K.
What's
I haven't
going on
seen
that's
it.
not reflected by the WWV numbers?
If there is, I couldn't speak to it. I don't really track them. I mean, I look at them every day, but I don't really track them in a meaningful way. I'm sure people do. I'm just probably not the person to ask about that. But there's more to it. I mean, there's all kinds of things that could be happening. You know, and honestly, this whole rebirth of HF is problematic in that if we do have a lackluster solar cycle, or God forbid we have, you know, another minimum like a Manger or Dalton minimum, that's going to kill HF. I mean, not just for hams, but for everybody. So we're all kind of, at least Rhode Schwartz, we're all crossing our fingers going, please have this be a killer solar cycle. So people say, yes, HF works great. You know, we could do nothing about that, but we try.
So I'm going to be very vague, but there are plans in place that would function well for the military, even in poor long range beyond line of sight conditions.
Yes.
Like they've thought of that.
Mm-hmm. There's also a lot of interest in things that like NIVIS, for example. NVIS has been really a huge topic for them because suddenly they realize, you know, I did a whole separate presentation on NIVIS, but and I didn't mention it in this one for that reason. But if I want to communicate with like squads in a small area and I don't know where they are, right? So I can't use a directional antenna. I can use NIVIS even in very challenging terrain to communicate with people over a radius of like 100 kilometers or so, even if I don't know where they are and they're on the move. So NIVIS has become very interesting for a lot of our customers. And again, NIVIS is not terribly limited by propagation, you know, solar cycle, kind of works all the time.
Yes, we've seen that as well. And then you can even do more interesting things with more exotic type antenna structures and things like that that do lead to small troop engagement in order to maintain contact in a more flexible environment.
Yep. So yeah, they're very, if you ask me what they're interested in Skywave and global, but they're probably, my feeling, again, based on my, is about equally interested in NIVIS. I mean, that's a hot topic for them. Yeah, and wideband HF is the other one that's a really hot topic for them.
Question, Paul?
Please.
Hi. You may have addressed this earlier. I got here late, but what's happened to all the international broadcasters? Radio Australia, VOA, Voice of Nigeria. We've got, some of us are shortwave listeners from way back. We've got QSL cards from all these guys, and they're not around. Is the internet taken over, and is the band space that they used to have going to be given to amateurs? What's going on with all that?
Well, I can't speak to the allocations part of it, but it's just, I mean, I was a shortwave listener. I mean, that's how I got into RF, and that's how I became an engineer, right? I was a shortwave listener as a kid. You know, I grew up in I'll call semi-rural South Carolina. There wasn't a lot of access to information other than shortwave. But that, I think it's basically the issue that everybody's got connectivity now. I mean, even the people in the most remote parts of the world have a cell phone. Before you wanted to find out what's happening in some parts of the world, you listen to, you know, VOA, or you listen to, you know, Radio Canada International or Radio Moscow, or, you know, their Deutsche Welle, right? I mean, you could listen to these folks, and I think that need has gone away. It's not that people are trying to force them out. It's just people are getting their news in different ways, and it's kind of killing HF. I'll give you my personal prediction. By the way, this is me as a person, not me as a Rode employee. I think broadcast TV is going away. I think long-term broadcast, what we call broadcast TV, is going to disappear because people simply don't watch it anymore, and that bandwidth could be better used for. Okay, other
Well-
people would like to use that bandwidth for other things. So,
I
sorry, I got to be careful what I say here. But I do think. Please.
K3ZO, I can say something about the VOA, but go ahead and finish what you were going to say.
Well, no, I was just going to say, I think broadcast AM FM radio will always stay around. It has a usefulness that's huge compared to the bandwidth it consumes. But I think broadcast TV is eventually going away, and I think that HF broadcasters went away because nobody was listening to them anymore, not because they were being pressured or somebody's trying to steal the spectrum for something else. But again, I don't work, so Fred, maybe you can chime in here.
Well, I had my career was with the Foreign Service of the U.S. Information Agency, which at the time also included the Voice of America. And Ken K4ZW, former KE9A, who I'm hoping will be able to get on one of these sessions next time. His whole job now is flying over to Africa and getting assignments for 1 kilowatt local FM broadcast stations on the regular FM broadcast band in each capital city. And then they satellite VOA programming to those stations in each African nation. And the whole idea is that your so-called opinion leaders, in other words, the people who are running the governments in each of these countries, as they're being driven to their offices in their chauffeur-driven BMWs and Mercedes, can listen to VOA on the local FM band. And so Ken's whole job is to fly to Africa and get assignments, frequency assignments from the local authorities in each capital city of each African country. That's what he spends his time doing these days. So basically the short waves are not required. They satellite the signal to the FM station directly, and then the FM station broadcasts it on local FM in the local African capital.
Great, that's fantastic information. Thank you for sharing that. That makes complete sense to me. I think that again, as the terrestrial infrastructure gets pushed out further and further, and by that I mean power, internet. If you're gonna have a little VSAT, you still need power. I think you're starting to see less and less use of things like shortwave, even XM radio. People talk about XM being satellite radio. In most parts of the United States, when you're listening to XM radio, you're listening to a terrestrial repeater. You're not listening to a signal from a satellite. And I just think that over time, the over the air is becoming closer and closer to the ground, and it's only going wireless for that last little hop to you. It's not being transmitted around the world via RF.
The only trouble is that Ken has is that he's arranged everything with the frequency people in the country involved to get a channel, and then somebody in the State Department spokesman complains about the human rights activities in that particular country, and suddenly Ken's pushed all the way to the back of the assignment system again as far as getting a FM station on the air in that country. So politics sometimes interferes with the technical part of radio.
That's why I'm an engineer, not a politician.
Well,
Are there any other?
in support of what you just said, think of the infrastructure cost and the ongoing operating costs of a 750,000 watt shortwave station.
Yep. I was heartbroken if you are just want to feel bad about life. When I watched the videos of them blowing up the VOA station, have you guys seen this? It's just heartbreaking to see those huge antennas being basically blown up. And but yeah, it's a huge infrastructure cost. So this is one of the reasons, incidentally, why HF is so hard to jam. If you want to jam HF, you're going to need something along those, that size and cost. So satellite, I can jam with stuff I have here in my office, right? If I want to jam HF over any meaningful range of frequencies and over any meaningful geographical area, I need a massive transmitter. So that's one of the reasons why HF is robust to jamming is you need those massive stations to do it. Or you need it over the horizon radar. That'll do it too.
It's still
Well,
fun to listen to. It was still fun to listen to each country's spin on the news, you know, and that's kind of gone. What you hear now on some of the shortwave bands is a lot of evangelicals, you know, that's big. Havana, Cuba is still on. I think they still have the same transmitter the Soviet gave them 50 years ago. It's kind of cranking away, you know, but not much left to listen to on some of those bands.
Yeah, it's a shame. I mean, you used to be able to, like, if you were interested in languages, right, you could write to, Radio Moscow, and they would send you booklets, and it took like months, and then you could like read the booklet and follow along with it. I mean, it's a fantastic resource. And again, I feel like it's been completely replaced by the internet. I mean, you can go to VOA's website and listen and download as podcasts their broadcasts. If I want to listen to VOA in Turkish, right, I can do that. I don't have to get on the air at all. And frankly, as much as I love radio, I'm kind of lazy too. And if I want to listen to that, I'm just going to download it. So it's a shame. Yeah. I mean, I wonder how many, I mean, for me, as somebody who grew up on radio and became interested in RF, and that's why I do what I do today, I wonder what the impact that will have on people going to STEM majors. I mean, how many people aren't going to get into RF because they didn't grow up with shortwave? But, I can't really answer that. But I miss it too. Other questions?
I did want to say on a positive note that we have seen that ham radio has a long pull through engineering and the government and other things. Like, we run into people, and I'm sure you do too, but you run into people who found you out or wanted to talk to you because they're an amateur radio operator, right? And they kind of find their way back to the amateur radio operators.
I always say that amateur radio is like the world's biggest fraternity, or it's like being a Freemason. You're part of this club, and immediately you have a rapport and something in common with someone when you meet. Oh, you're a ham radio operator. Oh my! And then all of a sudden, like, you're friends, right? You don't all the other stuff drops away, and you can just talk to people. I find. I'm sorry, Brett, go ahead.
It was very useful to me in the Foreign Service. Immediately when I had arrived at my new overseas posting, where I had friends that I could talk to and get to know how the normal people in that country think and work, instead of, having to deal with the kind of people that make it a point to get to know embassy people. It's not always for the best intentions.
Mm-hmm. Yep. Yeah, absolutely. I mean, I really feel like, again, working in RF for a living, I used to be surprised, and I'm not surprised anymore, how many hams I meet. And a lot of people, again, you get instant rapport, instant bond. I mean, I really, at the risk of sounding corny, I mean, I really think there is this bond in the amateur radio community, and having an interest in ham radio, I think, brings a lot of people together that might not otherwise have been brought together. And again, I love the fact that Dr. Rhode of Rhode and Schwartz is a very active hammer. N1UL. I mean, definitely you can get on 20 meter, 40 meters, you'll find him there. And he very much promotes ham radio, and it's wonderful. Even though as a percentage of our business, HF is not a huge part of our business. But it's great to see so many ham radio. We have a club station in Munich that we can operate, a really nice station. And it's like I said, I think it's something that brings people together.
Paul, thanks an awful lot. This is really good, and that was a great way of ending the session, because ham radio does bring us together. We're hoping that the technology will serve this generation and future generations. And I'm still probably more positive about the redundancy that HF can bring in a lot of places, including broadcast, but we'll see. Maybe I watch too many apocalypse kind of movies. I'm not certain. But anyway, thanks, Paul, and thanks everyone for joining us this evening. We'll get this up on our website in a couple of weeks. And everyone who's here, we hope to see you next month. Bring your friends and family. So everyone, have a good evening. Good night.
Thanks everybody.
Good night.